So let's do an example to find the solar azimuth and solar altitude for a specified location, date, and time. Unfortunately, these problems are a bit like a nesting doll, with equations within equations, but we'll try our best to chug along. The solar altitude depends on hourly, seasonal variations as well as our position on the planet, and we'll denote that beta, whereas the solar azimuth we'll represent with phi is the hourly variation of our sun's position east to west. To get started, we'll need to note that the latitude and longitude were given in both degrees and minutes of arc. But we'll want to convert the latitude and longitude to only decimal degrees. To do that, we'll multiply our minutes of arc by 1 over 60. Next up, we're going to have equations that require the day number of the year that's either going to be denoted N or capital D. For August 11th, the day number of the year, assuming it's not a leap year, is 223. This was found by simply counting up from the start of the year at January 1st to the date that was specified. Next up, we're going to need to calculate the declination angle, and that is the angle between the sun's rays and the equilateral plane. This angle changes throughout the year and is responsible for the unequal periods of day and night throughout the year. The equation is given by 23.45 degrees times sine of 360 over 365 multiplied by our day number minus 81. If we plug in our day number that we found above, we'll find that our declination angle is around 15 degrees. Next up, we'll need the EOT, or the equation of time. The EOT corrects the solar time for the shape and the angle of the Earth's orbit. This equation also has an intermediate variable denoted capital N that we can find with the day number of the year that we calculated earlier denoted small n. The equation itself is really long and not fun looking, but the calculation is rather straightforward. All we have to do is plug in our capital N and we'll find the value that we're after. Plugging in the value, we'll get a negative number of minus 4 minutes, which means you could think of it as if the sun was 4 minutes behind where it would be if the Earth's orbit was circular and uninclined. Next up, we'll calculate the AST, or apparent solar time, and to do that, we'll have to correct our LST, local time, by subtracting 1 hour since August is in the summer, which means there's daylight savings occurring. Then we'll be able to sub in the values that we found for EOT, the given LSM, and our longitude. And in doing so, we'll find that the AST, also sometimes called the true solar time, at noon local time is about 10 a.m. solar time. Next up, we'll need the hour angle, which tells us the sun's angular displacement from the local meridian, and is found using our AST. Now finally, after we found our hour angle, our declination, and converted our latitude, we can finally compute the solar altitude denoted beta. Again, the solar altitude depends on the hour, the season, and our position on the planet, which is why we had to calculate a whole bunch of previous variables to finally get this angle that helps define the position of the sun. We'll plug in our numbers, isolate for beta by taking the arc sine, and we'll finally get an angle that is around 48-49 degrees. The solar azimuth, which helps to find our horizontal position of the sun, requires beta, which is why we had to solve it in this order, but at last we have everything we need to finally compute the angle that we denoted phi. Similar to before, we'll plug in all our variables, our declination angle, our latitude, our hour angle, and our solar altitude, and we'll isolate for phi by taking the arc cos. In doing so, we're able to define the horizontal position of the sun at 134 degrees. To quickly recap what we did, in order to define the sun's position vertically and horizontally, we started by converting our latitude and longitude to decimal degrees. We then found our day number counting up from the start of the year, of which we could use to find the declination angle. We then found our EOT correction, and with that we could find our apparent solar time AST, making sure to correct for daylight savings by subtracting 1 hour from the local time. With our AST, we're able to get the hour angle, and with all of that we can finally compute the solar altitude, and lastly, the solar azimuth.